We go. We are into chapter 5 today. So math 95, 7:30, almost to the end of the month. Chapter 5.1, variation. Okay, so we've been talking about different types of mathematical relationships. Um, technically the four we've talked about so far are linear, which is when the input increases, the output is added to. I'm going to do that. So this is our verbal. And here's a little numerical representation. All right, we increase the input, and the output is added to. We've talked about exponential. When the input increases, the output is multiplied by a constant number. All right, so here's our numerical. We start at 2, and when we increase, we multiply by 3 each time. Logarithms is technically another mathematical relationship. Logarithm is the other side of the exponential coin. So I'm not going to develop that farther. I'm just going to recognize that we've talked about it. And then we talked about quadratic. Which is the output is determined by running the input through the quadratic function. That's a little bit circular definition, right? That'd be like me saying, well, and the exponential is determined by, the output is determined by running the input through the exponential function. That's a little circular, but we don't really have a better way to describe this. But if I have like y equals 2x squared minus 5x plus 1, there's not really this constant change either through addition or multiplication. We really just have to crank it through each time, right? So when x is 0, all this goes away and we have 1 right there. When x is 1, we have 2 minus 5 plus 1, which is -2. When x is 2, we're going to have 2 times 2 squared minus 5 times 2 plus 1, which is 8 minus 10 plus 1, which is -1, right? So you just kind of have to crank it through. And so now when we talk about variation, also known as power functions. The output is a power of the input, perhaps scaled by a coefficient. So that's what this chapter is about. The output is a power of the input and is perhaps scaled by a coefficient. So we're going to talk about three subtypes of variation. But first, let me show you an example. And we got x here, and we have y is 3 times x to the 5th. Right? The output is a power of the input, perhaps scaled by a coefficient. Notice how this is different from an exponential. In a variation question, in a power function, the variable is the base. In an exponential, the variable is in the exponent. That's the main difference. Totally changes the behavior of the system with one very small spelling change, you could say. Right. Go back to how important spelling is in English. All right, you change one letter, you're going to totally change what this sentence means. This means like, okay, it was kind of a frustrating day, but change that to a P, and it was a pretty awful day. All right, one little spelling can completely change the system. So if we were to put x 0, 1, or 2, y is 3 times 0 to the 5th, but that's still going to just be 0, right? If we put 1 in, we get 3, and if we put 2 in, we get 3 times 32, which is 96. So in that sense, it's kind of like a quadratic function. There's not this necessarily regular change from one to the other. You kind of just have to run that input through the function to get the output, but it's a very simple relationship between the input and the output. The output is just a power of the input, and maybe you're going to scale it by a coefficient. So we're going to talk about three types of variation. The first is called direct variation, also known as directly proportional. The second is inverse variation, also known as inversely proportional. And the third is varies it could be directly or inversely with a power of x, with the power of the input. So this is the most general type of variation. You don't care if it's direct or inverse. and it's whatever power it is. Okay, that's the question. That's the type 5 that I showed you here. Excuse me. Where it's simply a power of the input, perhaps scaled by a coefficient. That's your third type here, where we talk about it varying with the power of x. In direct variation, the power is just 1.
1 to 1.
1 to 1, basically. Yeah, or 3 to 1, or 10 to 1. But the power on the x is 1. In an inverse variation, the power is -1. It's a division. And in our third type, the power can be anything. It could be 2, it could be -2, it could be 1/2. That's pretty common. So let's look at each of these in turn. So direct variation. The time it takes to eat a hot dog is directly proportional to the length of the hot dog. Or you could say, AKA, varies directly with the length of the hot dog.
Your English thing came up again, because I see a lot of times it's as, directly as something. You know what I mean, sort of, the wording.
Yeah. So you would say the time it takes to eat a hot dog, what?
Well, it just, instead of the word, they word it differently, very directly, and then they also just very as or something.
Varies as the length of the hot dog. Yeah, okay, I see that.
That's
Yeah.
kind of confusing.
Yeah. So for example, a 4-inch hot dog takes, now we're talking about championship hot dog eaters here, okay? Not you and me. 10 seconds to eat. I bite, chew, swallow, bite, chew, swallow, bite, chew, swallow, bite, chew, swallow. On the 8-inch hot dog, how long do you think that would take to eat?
Longer.
Yes. It varies directly. It's directly proportional. So if a 4-inch hot dog takes 10 seconds, 20 seconds, exactly. Right? It's simply a multiple of x. The output is a constant multiple of the input. This is what it means to vary directly. The output is a constant multiple of the input. I'm going to do this. This is the verbal. Now I'm going to do it numerically. So we've got hot dog length, which is our x, and time to eat, which is our y. And we know, I'm going to leave some space, leave yourself a little space, okay? 4-inch hot dog, inches, seconds. The 4-inch hot dog takes how long? 10 seconds. An 8-inch hot dog takes how long? 20. How long would a 6-inch hot dog take? 15, exactly. How long would a 2-inch hot dog take? 5. How about a 1-inch hot dog? 2.5, right? And a hot dog at 0 length? Exactly. And that's not just mathematical, that's also logical. right? Notice this value right here is 2.5 times 0. This is 2.5 times 1. This is 2.5 times 2. This is 2.5 times 4. This is 2.5 times 6 and 2.5 times 8. Y is 2.5x. It's simply a constant multiple of the input. If I were to show you as a graphical, where here's X, which is hot dog length, and Y, which is time to eat, where would the Y-intercept be? On this graph?
0.
0, 0. Right, and we see that on our table, the Y-intercept is the output when X is 0, 0, 0. Every single variation question has a 0, 0 Y-intercept. Even if it's inverse variation, even if it's varying with to a power, it always has 0, 0. The time it takes for an object to fall, that's not direct variation. It actually varies with the square root of the height. But nevertheless, if the height is 0, how long is that pen going to take to fall? 0. Every single variation relationship goes through the origin, and in direct variation, it's just a straight line. Slope is 2.5. Right? And that's exactly what the formula y equals 2.5x gives you also. So direct variation, for me, the hardest part of direct variation is it's like something really simple wrapped in a lot of fancy clothing. Right? Honestly, all we're saying is the output is 2.5x. When we say it varies directly, it's directly proportional to the length of the hot dog, and a 4-inch hot dog takes 10 seconds to eat, that's a lot of fancy ways to say y equals 2.5x. And now you know that a champion hot dog eater, if they had to eat a 100-inch hot dog, you would know it would take them 250 seconds. Except, of course, this model is going to break down. Because if you gave a champion hot dog eater a 1,000-inch hot dog, do you think they could eat that in 2,500 seconds? Probably not, because the 1,000 inches of hot dogs probably weighs more than they do. All right, so the model's going to break down because every model breaks down at a certain point. That's direct variation. Here's a type of question you might see in your homework. So I want to show you, not because I think these are super awesome questions, but they do appear sometimes. Let's see. A varies directly with B, and when B equals 5, A equals 30. What is the value of A when B equals 12? Let's talk through the steps. Step 1, always the first step, is what is the function that describes this system? And actually, that was one place on the midterm that caused some challenges. I asked a question about an alligator swimming toward a dock. And because we had talked a lot about exponential functions, a number of students were like, exponential function. But the first step is always, what is the function that describes this system? That alligator was swimming at a constant rate. That's a linear system, right? So you still want to start with what is the function that describes the system. You have some nice clues right here. It varies directly. So this is a variation question. And in fact, it's a direct variation question. Step 2, what is the formula for a direct variation question? It's simply y equals m times x, where m is the slope. Just like we had here, all of that work just to get to y equals 2.5 times x. There's our graph. The slope is 2.5. There's no constant term added or subtracted. So step 3, figure out the values of the letters. In general, in mathematics, these letters are called parameters. They are the numbers that give you the structure of the system. In this case, the only letter we're trying to figure out is M. And we have some information. We know that when B is 5, A is 30. Oh, sorry. In this case, if it's y equals m times x, that means A equals m times B, right? Specifically to use our letters. But I think it still makes sense to start with this general y equals m times x. And you know that if A varies with B, that means B is the input and A is the output. So we knew that 30 equals m times 5. How do you figure out what m is? Divide both sides by 5, and you get m equals 6. Now you can complete the function. A equals 6 times B. That's an issue because my 6's can look like my B's. And finally, we can answer the question. When B equals 12, A equals 6 times 12, which is 72. I hope that you recognize the consistency for solving these questions. Whenever you're given a verbal representation of a mathematical idea and asked to do something with it, the first question should always be, what is the system? What is the function that I'm working with? Because if you want to use a symbolic representation, you need to use the symbol that represents the same situation. So you have to be able to pick what that is. And we've seen in this class, sometimes it's linear, sometimes it's exponential, sometimes it's quadratic, and now it's a variation question. Okay. Any questions? Let's talk about inverse variation. It's very similar, but now instead of y equals m times x, it's y equals m divided by x. This is no longer linear. This is called a rational function. Rational means fraction. It's a function built off of fractions. You still have an input, and you still have an output, and you have a coefficient. This is not going to be called the slope anymore because it's not going to be a straight line if you graphed it. Let me think of a good one. Uh, here we go. Joey's boredom is varies inversely with the number of friends he has. So his boredom index, right, just some random number to kind of give you a sense of how bored he is 10 when he has 2 friends. His friends come and go, they move away, they get new jobs, they have a fight, meet someone at the bowling alley, makes a friend, right? The number of friends Joey has fluctuates, which affects his boredom. The more friends he has, the more stuff he has to do. So let's put this in a table. Using the varies inversely, right? That's our step 1. So let's explore this a little bit. X is the number of friends. Y is this boredom index. Bigger numbers mean he's more bored. Smaller numbers mean he's less bored. So Joey has 2 friends. His boredom index is 10. And we know that's going to be M divided by 2. So what is M? 10 is M divided by 2. So you're saying M is 5. 5 divided by 2 is not.
2 divided is 10.
Let's try 20. Because if M is 20, we get the 10 that we wanted. Yeah. Let's add another friend. All right. So that's going to be M over 3. And let's add another friend. That's going to be M over 4. Let's take away a friend. Catania just moved to Albuquerque. So there goes his golfing buddy. Boredom index is going to go up. All right. So if 2 friends means he has a boredom index of 10, then yeah, I would say M probably is 20 because 20 divided by 2 is 10. So 3 friends, that would be 20 divided by 3. And 4 friends would be 20 divided by 4, which 10 happens to equal 5. That one's a decimal. Notice the more friends that Joey has, the less bored Joey's going to be. What if Joe only has 1 friend? He's got a much bigger boredom index. What if Joey had 0 friends? What's the mathematical thing we're going to try to do?
Not going to be bored.
M over 0. Can you divide by 0? No, 20 over 0, can't do that. So in an inverse variation, you can never put x equals 0 into there because your system breaks down. And that's okay. There are lots and lots of physical systems that break down when the input equals 0. Let's put this on a graph. This graph's a little trickier to draw. There, 1, 2, 3, 4, 5, 6. 20 over 6 is about 3.3, right? Yeah, about 3.3. And 20 over 3 is about 6.6. Okay. All right, so here's 20. When x is 1, y is 20. Here's 2. When x is 2, y is 10. Here's 3, that's going to be about 6.6. Here's 4, that's going to be about 5. Here's 5, or exactly 5. Here's 5 is going to be 4. 3 is going to be... So what you end up getting is something that looks like this. It's not exponential because it never touches the axis. It kind of looks like an exponential. I'll acknowledge that it kind of looks like an exponential. But this is a rational function. It never touches the y-axis because you can't divide by 0. And it smooths out, right? As Joey gets more and more friends, what happens to Joey's boredom? Gets smaller and smaller. It's never being negative because there's no such thing as negative boredom. Everybody always has a little boredom in their lives. So direct variation is a nice straight line. Usually goes up. Crosses through the origin. Inverse variation has this kind of C cupped shape. And there are a lot of systems that actually have this sort of shape. I'll give you an example of a question you might run into. P varies inversely with R. And when R equals 3, P equals 12. What is P when R equals 10? First question, I want you to not answer this out loud, but I want you to write down an answer on your page so you can check it later. Is make a guess. If R goes up to 10, is P going to be larger or smaller? Write down the word larger or smaller, whichever you think it is. But don't tell me, don't tell anybody else. Step 1. What function? This is an inverse variation function. And we have that nice clue right there. It says it varies inversely. Step 2. The function should look like y equals m over x. And in our case, which letter is y? Yeah. Y is going to be P. So the input is going to be R. This is normally how we would interpret that. The truth is, mathematically, it wouldn't matter if we switched them, because it's a very, very simple relationship. So there's our function, P equals M over R. So now we're going to figure out what M is equal to. Because we know that P is 12 when R is 3.
40.
No, but you have the right idea. Your arithmetic went a little haywire. $36. M is 36.
The letters all messed up.
This is the other thing, especially with blame physicists, because they love to give letters to different things. Mathematicians will happily use Y and X and only those forever, because we don't care. We all know they're variables, so why not just pick two variables and stick with them forever? But physicists, they come up with a different letter for everything. Mass has a letter, velocity has a letter, speed has a letter, time has a letter, inertial moment has a letter. Yeah, they all have different letters, and then they just all get mixed around. Yeah, it's not awesome, but so it is. So step 3, M is 36. So now we rebuild the function. Y equals, not Y, sorry. P equals 36 over R. So step 5, P is going to be 36 over 10, which is 3.6. Is that larger or smaller than it was? Smaller. Which makes sense because it varies inversely. As the input gets bigger, the output gets smaller. That's what it means to vary inversely. Okay. All right. So now we look at our third one, varies with a power of X. The output varies with a power of X. That power can be 1, in which case it's just direct or inverse variation. But there are a lot of things where it's not 1. So example, power equals 1. If I double the length of one side of a square, the perimeter will also double. So this, again, this is what we looked at our first example where the power is 1. So here's a square, side length is 1. What's the perimeter? Yeah, it's the distance around the outside is 4. 1 plus 1 plus 1 plus 1. Now I'm going to double the side length of that square. So now the side length is 2. What happens to the perimeter? It doubles. It's 8. Double what it was. So if I want to use S for side length and P for perimeter, P equals 4S is my variation. Now let's look at power equals 2. If I double the length of one side of a square, the area will be multiplied by, not going to double anymore. It's actually going to go up by 4, which is 2 squared. Going to be multiplied by 4. So let's look. Here's my square, side length 1. Area is 1 squared, which is also 1. If now I double that side length to 2, the area is now 2 squared, which is 4. It didn't, oh, side length 2, sorry. Doubled the side length, but I didn't double the area. I multiplied it by 4. But that does not mean area is equal to 4s. Because if I triple, where the side length is 3, what's the area going to be? 3 times 3. And so not the perimeter, which would be 12, but the area, which is going to be 9. So my relationship is area equals side length squared. It is now, area is now a power of the side length. Right? Let's look at, I just want to do one more, which is consider a sphere. And so there's my sphere. It has a radius. R is the radius. So we can talk about different geometric ideas with this radius. We can talk about R as a radius. We can talk about C, which is the circumference, which is the length of a circle around the sphere. We can talk about A, which is the surface area. All right, so if you shaded in the whole side of the sphere, right, it's a 3-dimensional object, but it has a surface area. And we can talk about V, which is the volume. So there are relationships, there are mathematical relationships for each of these. The circumference is 2 pi r. If I have a sphere, and I take the radius r, then this walk around the sphere is 2 pi r. This is directly proportional, right? C varies directly with r. Because that 2 pi right there, that's like your m. 6.28 something. The area is 4 pi r squared, the surface area. So A varies directly with r squared. If I increase, and that's just like the square, right? When we did the square over here, We said the area is the square of the side length. Area always varies with the square of your linear measurement. And the volume is 4/3 pi r cubed. Volume varies directly with r cubed. So that's how we talk about variation when it's not just a power 1. We get to still say it varies directly, but we have to specify that it's a power on the input. So let's look at what that would mean over here. Let's double r. Then we're going to double the circumference because it varies directly with r. But we're going to multiply the area by 4, which is that 2 squared. And we're going to multiply volume by 8, because that's 2 cubed. And we can also do this power variation inversely. That's actually not that hard to do. All right, last example. Which is variation with fractional powers. This still falls under that third category. Variation with fractional powers. The time it takes for an object to fall in Earth's gravity, ignoring air resistance, is time equals 1/2 times the square root of h. Is it 1/2 or is it 1/4? I better double check. I'm gonna leave it as 1/2. Because I don't think it is. I think I'm up to 1/4. Give me 1 second. Please don't want to give you wrong information. One quarter. That's 1/4. 1/4. So it's 1/4 times height to the 1/2. This is still a variation question. All right, so you would say time varies directly with the square root of height. So let's build up a table that is gonna make a little bit of sense. There's some units here that I'm not gonna worry too much about. X equals height, Y equals 1/4 X to the 1/2, which is time. So if that object is 0 meters above the ground, how long is it gonna take until it hits the ground? So let's not do ground, let's do table. So the pen is 0 meters above the table. When I release it, how long does it take to hit the table? Go ahead, Lisa. 0, lose 0, yep. I didn't get your name wrong. I was just talking to Lisa behind you, but that's great. All right, it doesn't take any time at all. Remember, for direct variation, you will always go through the origin. Now, if I raise that to 1 meter, it's going to take about 1/4 of a second. Because that's 1/4 times 1 to the 1/2. If I raise it to 2 meters, it's not going to take half a second. It takes less time. It's going to be 1/4 times 2 to the 1/2, which is, about 1/4 times 1.14. 1.41. 414. Which is 0.35 seconds. I doubled the height, but I didn't double the time. If I do 3, it's going to be 1/4 times 3 to the 1/2, which is 1/4 times 1.7 approximately, which is 0.433. You still fill out your table just by plugging your input through, but it's not increasing at a constant rate anymore. If you were to graph this, what you would find is when your height is 0, of course, it takes 0 time, and you increase your height, you increase your time, you increase your height, you still increase your time, but by not as much. And you do it again, and you do increase your time, but again, by not as much. So what you end up getting is something that kind of does that. Y equals 1/4 X to the 1/2. There's 1/4. So we can do all kinds of variation. We can do it with powers of 1, or we can do it with powers of -1, which is dividing. But we can do other powers. We can do powers 2, power 3, power 4, and fractional powers. We can do 1/2, 1/3, 1/4 with the input either on the top or the bottom. And with that limited set of components, we can build a lot of different physical systems. Physics relies heavily on these power functions, on these variation pieces. In a lot of different ways. You'll see that, especially as you move on, either if you take physics or in later math classes, that these pop up again. Okay, that's all the information I have. I think it looks like I might need to print off a couple of worksheets, at least 2. So I'm going to go do that. And otherwise, it's still worksheet week 6. So you can continue working on that wherever you left off. I'll be back in a minute once I print things off, and then I'll also have to finish the key. But you can hold on to this for now, in case anybody has questions.